So the purpose of this lab was to analyze the motion of a spring mass system with the mass isolating in an arc. I used Tracker to observe the position and GlowScript to create a computational model predicting the ideal motion. The goal was to determine whether the computational model followed the energy principle. So the key physics principles in this lab were Newton's second law and the energy principle. Newton's second law states that the system's change in momentum is proportional to the net force applied. And the energy principle states that a system's energy change equals the sum of work done by external forces in the thermal energy exchange. So the forces acting on the mass include the upward force of the spring and then the downward force of gravity. And net force is the sum of these forces, which can be expressed mathematically as shown. And the system's components were the mass, the spring, and the earth. And the energy components are the kinetic energy, gravitational potential energy, and spring potential energy. Since the system is isolated, the total energy should remain constant. So this video right here shows the mass, the tracker data showing the observed motion. The object had a mass of 0.402 and a stretched spring length of 0.7, and it was dropped from rest with an initial velocity of 0 meters per second. So now we can move on to coding. First, I put the initial conditions from the tracker data, such as the mass of the ball or of the weight, and then the position of the mass and the velocity of the mass. And then I also calculated the spring's length and direction. And then I also went on to calculate the system's kinetic, gravitation, and spring potential energy using the equations shown. Then, in a while loop, I iterated through time steps to calculate the specific energy changes. And first, I did that by defining the force of gravity vector and then the force of the spring, and used that to calculate F net. And then I used the momentum principle to update the velocity and the position over each time step. And then after that, I calculated the energy changes. So I calculated delta K, delta UG, and delta US. And then I added those all together to calculate the change in energy. So here is my data for the model. So as you can see, my exposition over time is pretty accurate, I would say, for the most part, but I wasn't able to get the Y position versus time graph to look accurate, and I'm not quite sure why. I spent a lot of time on my code trying to find specific mistakes or bugs. So if you guys saw a mistake, please let me know, but I'm genuinely not sure why I wasn't able to get my Y position graph to look right. But overall, I would say that the model followed the experiment semi-well. So next is the energy principle satisfied. So in our model, no external forces act on the system, meaning the total energy should remain constant. And I think that my graph actually does confirm this. You can see there's a bit of discrepancy. The delta E is going a little bit up and down, but I would say for the most part, the change in energy was pretty much zero. So I would conclude the energy principle is valid. Now we can talk about comparing oscillation periods for X and Y directions. So to get the oscillation periods, I simply just looked at the peaks for each graph, for each X graph and Y graph in the tracker data. And for the X direction, I got T equals 1.614, and then I just used this to calculate K. And then I did the same for the Y, but instead with T equals 1.51. And as you can see, there is a pretty big change in the K stiffness. So it does matter which one you choose, because the results show two different periods for X and Y directions, which affects the calculated spring constant and the graphs. So that's it for this lab. Thank you so much for listening.